So this is a project with my supervisors, Damon and Simon, who's in Nancy, Simon Perdry, Alex Kissinger from the University of Oxford, and Clément Mignon, who is also a PhD student at l'IPSIS with me. It came out of a talk I gave last year at QPL on flow conditions and convergence of CV, continuous variables measurement-based quantum computing. After that talk, Alex got in contact with me because he had a very similar way of talking about MBQC with Qudits to what I presented there, and this is what came of that discussion. So causal flow and its generalized flow were originally introduced, as we're going to see, to treat the problem of determinism in measurement-based quantum computing. And what I mean by that is that in measurement-based quantum computing, as opposed to the quantum circuit model of computation, we use measurements to implement transformations. And these measurements are inherently probabilistic, which leads to a random outcome of the computation. And the question then is, how can I use corrections which depend on the outcomes of those measurements to map my probabilistic computation back to a deterministic one? Now, although that was the original motivation of flow conditions, what's interesting is that they have gone on to be applied to a pretty wide variety of problems. These are just a few examples. For example, they've been used to parallelize quantum circuit by reducing the depth, to reduce the depth of computations. They've also been used in the graph theoretic, or in the simplification of quantum circuits, because they serve as as far as I know, the most general method for extracting quantum circuits from ZX calculus diagrams, if you know what that is, which led to, at the time, state-of-the-art extraction algorithm, simplification algorithm, although these things never stay state-of-the-art for very long. And then just a little bit of self-publicity. This is the talk I was mentioning at my title slide for where I used flow conditions to treat the convergence of continuous variable measurement-based quantum computing when finite squeezing resources are considered. Now, diving straight into the subject, the state space of a qubit is a d-dimensional Hilbert space, which furthermore has, as a result, a basis of size d. But we further impose in this talk that d should be a prime number because that makes ZD into a field, which is an important property, or has important implications that I won't particularly go into. And in fact, we also assume that D is odd for more complicated reasons that I won't go into. Now, to manipulate the state of a qubit, we have Pauli gates, or the generalization of Pauli gates from the qubit case. Here, the Z operator acts as multiplication by a dth root of unity, which we know omega, weighted by the label of the basis element it's acting upon. And X, the X gate acts as translation the translation between the different elements of the basis. From these two operators, we obtain what we call a Pauli, or a generic Pauli, as just any product, ordered product of these two operators, where the weights, the exponents come from the field that we're using for our model. Now, these Pauli operators are further linked by the Hadamard gate, or the discrete Fourier transform gate, which is just the straightforward generalization of the Hadamard gate for qubits, but as you can see, maps the Z gate to the X gate. And as sort of the final piece in terms of gates that we're going to need, we need a gate that we use to generate entanglement. In our case, we use a generalization of the controlled Z gate, or controlled phase, which, just like the Z gate, acts here as a multiplication by a dth root of unity, weighted again by the labels of the basis states on which we're acting. Now, a key difference from the qubit case is that these operations are no longer self-inverse, and this is going to come up in a couple of slides later in the talk. But they verify instead these relations here, where I use 1 to denote the identity operator on the Hilbert space. Now, measurement-based quantum computing, the simplest form of a measurement-based quantum computation is the gate teleportation that I'm sure many of you are familiar with. This is the gate teleportation protocol for Qudits. And the idea is if I have some input state psi onto which I would like to apply a unitary, here u, I can do this by entangling psi with some auxiliary state via my controlled phase operation, and then performing a measurement in a basis that corresponds to the unitary that I'd like to implement. And then by performing a correction on the auxiliary state, which depends on the outcome m of the measurements, then the output of this circuit is precisely the unitary applied on my input psi up to some Hadamard gate, which I can get rid of later if I need to. Now, this isn't the only example of teleportation protocols. This is essentially a gadget protocol for the unitary u. The idea now is that instead of measuring psi, I measure the auxiliary state. And once again, by doing a correction, which this time is different than in the top circuit, I'm going to manage to implement a unitary u here on my input. And this leads us to the first problem for trying to reason about measurement-based quantum computing in full generality for Qudits, is that we need to be able to consider all of these kinds of protocols in one framework. And so the first thing that we need to do is we need to figure out what kinds of measurements precisely I can do for which it is still possible to obtain this deterministic outcome, this unitary output. Because although I haven't gone into the details, the unitaries u in the top and bottom circuit each have to verify specific properties for the circuit identities to hold, and furthermore they're different for the top and the bottom circuit. Now this is complicated a little bit by the fact that since the Paulis are not self-inverse, they are also not self-adjoint, and so therefore in principle they don't represent measurable quantities or observables in quantum mechanics. And in the case of Qudits, the Bloch sphere is not a particularly intuitive object. So instead, it turns out that the correct definition, or the good definition to make is the following. For a fixed Pauli Q, we define the measurement space associated to Q to be the set of fixed point unitaries M such that M omega commutes with Q. Now, the fixed point condition just says that M has an eigenvector associated with eigenvalue 0, and the reason that we do this is because we need to have an outcome for our measurement which is preferred, which is going to be the one that we're going to try and map everything back to throughout our correction procedure. Now, the key implications of this definition are the following. Firstly, if M is a measurement in the measurement space of Q, then M has d eigenvalues, and these are the dth roots of unity. And furthermore, Q translates between the eigenvectors which are associated to these eigenvalues. And this means that in some sense, I'm going to be able to use Q to perform corrections when I get a measurement outcome which isn't 0, which isn't the desired measurement outcome, right? And secondly, the other key implication is that any two measurements in the measurement space of Q are related by a special unitary here, u, which furthermore commutes with Q. And what that means is that if I fix a reference axis for each measurement space, then I can identify each measurement in that measurement space simply by the angles of the special unitary rotation in that, with reference to that axis. And so that allows us to parameterize all of our measurements by a set of angles. Now, this allows us now to present the formalism for reasoning about MBQC. And so we call a measurement pattern on a set V of Qudits is essentially a list of commands taken from the following set of operations. Firstly, we have an initialization procedure, which simply initializes the Qudit in an auxiliary state, which here is the Qudit generalization of the plus state. Any Qudit in V which is not initialized is considered as an input, and so any implementation is expected to have an input psi on which to apply the measurement pattern on the non-initialized Qudits. We have the entangling operation, which is simply which simply applies our controlled phase on a pair of Qudits u. A pair of Qudits u and V with some exponent lambda. We have a measurement command, which here performs a measurement in the measurement space associated with the Pauli XAZB, with the corresponding angles. And then finally, we have Pauli corrections, which here depend linearly on the outcome m of the measurement of a single vertex v. Okay? So a key result given this setting of measurement patterns was proved by Vincent Darno-Salahem-Kashefi and Prakash Panangaden. In the case of qubits, but generalizes very easily to the case of Qudits, is that any measurement pattern with some additional sort of causality axioms imposed on it can be rewritten in the following form. Firstly, we perform a set of initializations. We then perform a bunch of controlled Z entangling operations, and then on this prepared state, we perform a sequence of measurements followed by corresponding corrections for that measurement, for the outcomes of that measurement, where here these X and Z gates act on multiple Qudits, but are separable Paulis. And what this means is that to this resource state here of the prepared and entangled, and consisting of the preparations and entanglement operations, I can associate a graph state, which is a very straightforward generalization of the usual Qudit graph states, where each of the Qudits V in my register is associated with a node in the graph. And for each of my controlled phase operations with a given weight, I draw an edge in the graph which is weighted with the corresponding element of ZD. Okay? And then we have some notation here for which nodes correspond to inputs, which ones are measures, and which ones are left as outputs of the computation, which are not particularly important here. Okay, so we've presented our framework for measurement-based quantum computation. Now I need to tell you a bit about outcome determinism. Now, in general, a measurement pattern is going to correspond to a quantum channel which acts on my input state here, rho. And it has essentially a branch map in its Krauss decomposition, which for each measurement outcome of all the measurements I perform in the MBQC. Now, we say a measurement pattern is deterministic if the output of this quantum channel doesn't depend on the measurement that I've made, the outcomes of the measurements that I made. And what this translates to is that each of the branch maps AM need to be proportional. Now, this is not a strong enough determinism condition, it turns out. There are pathological edge cases that we want to exclude. And in particular, it is not a sufficient condition to imply that the computation that I implement is an isometry. That is, there are measurement patterns which are deterministic but do not implement isometries. And so to circumvent these pathological cases, we introduce a stronger determinism condition, which essentially says that rather than just being proportional, all the branch maps need to be equal up to a phase. And then finally, even this is not a strong enough determinism condition for the characterization of determinism that we have done. We further impose that, we further say that a measurement pattern is robustly deterministic if it is uniform, that is, it is deterministic for any choice of measurement angles for any of the measurements. And furthermore, it is stepwise strongly determinism, that is, any partial computation is deterministic, or if I stop at any point during the MBQC, the resulting computation is going to be deterministic, right? Okay, so now we can dive into flow conditions. And I'm going to do this essentially graphically by reasoning on the graph states. And the first thing that we need to consider is what is the result on my graph state if I perform a measurement in some measurement space here associated with Q and obtain outcome M. Now, as I said a few slides back, I define, so the measurement associated with M is going to correspond to the projectile valued measure of its spectral decomposition, right? And as I said before, the eigenvalues, the eigenvectors of M are translated between by action of Q. And what this means is that when I perform this measurement with outcome M, I can view this as if I had obtain the outcome 0 here, but with my operator Q acting before the measurement is made. And so if I can get rid of this operator Q, this error Q on my graph state, then I will have succeeded in obtaining my deterministic computation. Now the problem, of course, is that once I've measured my system, I have destroyed it and I no longer have access to it to perform this correction. So the way that we get around this problem is by using a standard tool from graph states. We use graph stabilizers. Now, the graph state here, or any graph state as we've introduced them, is stabilized by the following operation. If I apply x on some non-input node and an operator z on every one of its neighbors, all with the same weight, then this is a stabilizer of the graph state. That is, it's equivalent to having done nothing on the graph state. Now, as written, this isn't a particularly useful operation until I start to do partial graph stabilizers. Because if I do this, I just do these two operators in part of a stabilizer, then I can identify the identity with z times its inverse, simplify by the stabilizer, and I manage to implement a z correction on my measured node which acts before the measurement is made. And so by using these kinds of operations, I can actually get at the measurement before the system acausally is destroyed. Now, the second ingredient to note for these partial graph corrections, so these partial graph stabilizers, is that the corrections are linear with respect to the edge weights of the graph. So here, if I perform these two partial stabilizers on the graph state, then the resulting correction on my measured node is going to be linear with respect to the edge weights. Furthermore, there are versions of these partial stabilizers where I omit the x operation, and this allows me to implement an x correction by doing partial stabilizers. And so through this method, whoops, I didn't notice I skipped a slide. Through this method, I can act as any Pauli on my measured node before the measurement is made, so long as the topology of the graph allows it. Now, how do I determine if the topology of the graph permits me to do this correction? Well, this is where the flow condition comes into play. And so a simplified version of our flow condition is as follows. We say that the open graph G, or the graph state, has a flow if there is a lower triangular square matrix C such that the product of the adjacency matrix of G times the correction matrix C is lower triangular. Now, this isn't a particularly clear statement as written, but it's actually, I think, pretty easy to understand if we look at a simple example. So this is a very simple graph state, which has a flow. This is the adjacency matrix of this graph. It has a flow given by the following matrix C, because if you perform the matrix multiplication, then you'll see that both C and the product are lower triangular matrices. Now, how do I interpret this flow condition as a correction procedure for an MDQC or for a measurement pattern? The idea is that here the matrix C corresponds to X operations acting on the graph state. And mapping them linearly through the adjacency matrix of the graph, I get the corresponding Z operations, right? Now, then, furthermore, each of the columns of C corresponds to a node in the register V. And in particular, and I interpret the order of the columns of C as the order for measurements of my nodes in the graph. Now, for a given column of my adjacency matrix C, the lower triangular operations correspond to corrections that I'm actually going to implement for a given measurement. And then the sup diagonal, or elements above the diagonal, correspond to the back actions that these measurements are going to have on nodes which have already been measured. And so this is where the lower triangular condition comes into play, because I don't want to reintroduce an error onto a node that I've previously measured when I'm performing the correction for a measurement further on in the procedure. And then the final ingredient is that the diagonal elements correspond precisely to the operation which I'm going to implement on the measured node, or the node that I'm measuring at that step in my measurement pattern. And so these need to correspond to the labels of the measurement space that I want to implement. So here what this says is that I'm going to implement on my first node the correction x to the power 0, z to the power 1. And on the second node, I'm going to implement the correction x to the power 1 and z to the power 0, and so the measurement spaces need to correspond. Now, there are other conditions that the flow needs to verify on this graph state, but they are not particularly interesting, so I won't go into the details. Now, given this definition and these considerations, our main results are the following two statements. Firstly, and this is more straightforward of a statement, we showed that if we have an open graph with ZD flow, then the MBQC, or the measurement pattern that I've just described, is robustly deterministic, and it implements a isometry which acts from the input to the outputs. Now, the, I think, more interesting statement is the converse result of this, which says that a measurement pattern that takes the form that I described earlier, in terms of the operations that I described earlier, is, if it's runnable and robustly deterministic, this runnable condition is just the causality considerations which are necessary for the Keshefi-Danos argument to go through. If an MBQC is therefore runnable and robustly deterministic, then it has an underlying open graph, and this underlying open graph has a ZD flow. So we can essentially say that in the setting of these measurement patterns that I described, for prime dimensions, MBQCs are robustly deterministic if and only if they have a ZD flow. So the converse of the converse theorem is a considerably harder theorem to prove. It involves using a fairly complicated lemma that has a proof, which I think we've managed to eventually reduce down to a 7 or 8 page proof. But this theorem was claimed in the original G-flow, generalized flow article for Qudits, but omitted part of the proof, was later corrected by the original authors, although I don't think that the correction is, as of yet, available. Now, we also have a handful of auxiliary results. Firstly, we have a polynomial time algorithm for finding a ZD flow for an open graph whenever it has one. And furthermore, this ZD flow that the algorithm finds is optimal in the sense that whenever measurements of corrections can be performed simultaneously, the output F flow does so, or the MBQC, the measurement pattern, does so. And so there are no measurement patterns that run in a shorter depth in terms of the number of measurement operations that you need to do. Then secondly, we have some results on how to manipulate ZD flows while preserving the semantics or the underlying computation which is being implemented. So we have results on how to connect two ZD flows together. If I have two graphs with their own ZD flows, how can I plug the inputs of one into the outputs of the next and obtain a ZD flow for the whole thing? Under what circumstances can I delete vertices in an open graph and maintain the existence of a ZD flow? And I think most interestingly, we show how to manipulate ZD flow under local Clifford operations. And this is interesting because essentially, if we want to obtain a circuit which implements our MBQC or our measurement pattern, if we want to obtain a circuit that implements the same operation as the isometry, which is implemented by a measurement pattern, then all of the extraction algorithms go via these local Clifford operations. Now, finally, we already have, as written, a circuit extraction algorithm, but only in the case when the measurement are all made in the measurement space of Z. And this was related to the work I did on CV flow and convergence of teleportation in continuous variables. So I suppose I've been a bit fast, but wrapping up, what we've left, what questions are left to answer for these kinds of measurement patterns is firstly, there's no known ancillary circuit extraction algorithm which works for all measurement spaces, so I'm currently working on doing this. And then there are generalizations of F-flow which loosen some restrictions on the types of measurement patterns which are allowed. So Pauli F-flow, which I've written, is one such generalization. There are others such as Pauli fusion flow, which sort of get progressively more complicated in their presentation. And then I think one last fairly major open question which remains is that what I've presented today only works in prime dimensions. It's fairly easy to generalize to the case where the underlying group is in fact a field, and that's where the name F-flow comes from. But if we want to take care of the case of MBQC in Hilbert spaces over any finite abelian group, the fundamental theorem of finite abelian groups says that such a group decomposes in a form as written here, but the F-flow condition only takes care of the factors where the cyclic group is over a prime number and not a power of a prime, and it's not clear how to take care of the power of prime factors in this decomposition. So yeah, that pretty much wraps up my talk.